Hello everyone and welcome to a new video. This will be the last new topic in this chapter and it's going to be about power. We covered the term power before when we studied it in the electricity chapter. But does it have a different meaning while we're talking about energy and work? Well, actually, yes, but slightly different. The concept is the same, but the meaning is a little bit different. So, we can say that the power is the indication of how much energy is being used at a certain amount of time. So power is very much related to time. The unit for power is called watt, and we already know that. And the equation used to find the power is the work divided by time. Or in other words, we can say it's energy divided by time. It's very similar to the equation we learned in the electricity chapter, but this time finding the work or finding the energy is going to be a little bit different. Now, we know that the unit of power is watt. We know that the unit of work or energy is joules, and the unit of time must be in seconds. So if we have any other unit, we must transform it into these three basic units. Another equation we can use to measure the power in terms of force and velocity, because in a lot of questions we have energy, we have force, we have velocity. So it doesn't always have to be using the same equation, which is work divided by time. We can say that the power is equal to the force multiplied by the velocity. So now we have two equations to calculate the power using. The first one we just saw it, it's work divided by time. The other one is simply the force multiplied by the velocity. And we know that the unit of power is what? The unit of force must be newtons, and the unit of velocity must be meters per second. Okay? Now, we must always keep in mind that we can use prefixes such as kilo, and kilo is very much used with watt. So 1 kilowatt is equal to 1,000 watts. Also, kilowatt hour, it's a commonly used term. So what does it mean? Well, it is how much energy is used by a certain device or a certain object every hour. So let's see, for example, if a device uses 200 kilowatts hour, this means that the number of joules will be found by multiplying 200,000 watts, because we have 200 kilowatts, which is equal to 200,000 watts, multiplied by 60 to transform the hours into minutes, and we multiply it by 60 again to transform the minutes into seconds, and we will get the amount of joules it uses every hour, which is indeed a very big number. So let's start solving some problems after we understood the main concept. First question, it says that 1 watt is equivalent to, and we have these choices. Let's remember what is the equation we used to find the power. Remember that what is the unit of power? So I know that power is equal to work divided by time. Let's see. The unit of power is watt. This means that 1 watt is equal to the work, W, which is in unit joules, divided by time, which is in seconds. So I can say that 1 watt is equivalent to joules per second, and the answer is D. Student A lifts a 50 Newton box from the floor to a height of 0.4 meters in 2 seconds. Student B lifts a 40 Newton box from the floor to a height of 0.5 meters in 1 second. Compared to student A, student B does, and we have these following choices. First of all, let's try to do the following. We will be finding for each student the amount of work or energy he used. Let's say work or energy. And we need to know how much power each one of them did. Now, let's start with student A. Now, student A is lifting a 50 Newton box at a height of 0.4 meters. So if you want to calculate the potential energy is equal to mgh, and remember that mg is the same as w, so we can say that the potential energy is also equal to w multiplied by h. So the energy that student A uses is 50 multiplied by 0.4, which is equal to 20 joules. So student A uses 20 joules of energy. Now, how much power does he use? We know that the power is equal to energy divided by time. So we can say that power is equal to energy divided by time, or work divided by time, which is the same thing. So in our case, it will be 20 divided by 2, which is equal to 10 watts. So student 1 does work equal to 20 joules, and he used a power of 10 watts to do this job. Now for student B, the same thing. We want to find the potential energy, but in this case we will multiply 40 newtons by 0.5 meters. 40 by 0.5 is also equal to 20 joules. But how much power has he done? Power is equal to work divided by time. So the work is 20 divided by the time, which is 1 second. So he is using 20 watts. Now let's go back to our question. It's saying that compared to student A, student B does the same work but more power, same work but less power, more work, less power, more work, more power. Well, in terms of work, they are doing the same work. So it's either A or B. It's not C or D. But in terms of power, student B uses more power than student A. He uses 20 watts of power. So the answer is clearly A. Next question. A 3-kilogram block is initially at rest on a frictionless horizontal surface. The block is moved 8 meters in 2 seconds by the application of 12 Newton horizontal force as shown in the diagram below. What is the average power developed while moving the block? Again, power is equal to work divided by time. And we know that work is equal to force multiplied by distance and divided by time. So we placed work with this equation, which is force multiplied by distance. So we can do the following. The force is 12, the distance is 8, and the time is 2 seconds. So the answer will be, we can do like this. It's 12 multiplied by 4, and the answer is 48 watts. So the answer is clearly C. Next question. Robert's mass is 55 kilograms. During a soccer practice, he runs up a set of stairs in 5 seconds. The total vertical height of the stairs is 6 meters. What is Roberto's power output in watt? Now, let's analyze this question. We have an athlete that is running up a set of stairs. The set of stairs is 6 meters high. Now, when he reaches this point, what type of energy does he have? Well, he has potential energy, and we can calculate this potential energy by multiplying his mass by G by H. Now, his mass is 55 multiplied by 9.8 multiplied by how high is he above the ground, which is 6. So we know that the amount of energy he used is equal to 3,234 joules. But it's not asking about how much energy is he using. It's asking about what is its power output, or what is his power output. We know that power is work or energy divided by time. So the answer is 3,234 divided by 5. And let's see our choices. The answer in our case is 646, and the closest answer is 647 watts. Next question. A boy weighing 500 newtons starts from rest, runs up a 5-meter high flight of stairs in 5 seconds, and stops at the top. The average power developed by the boy is most nearly. It's very similar to the previous question, but this time we do not have the mass. We have the weight of the boy, so we can say that the potential energy is equal to mgh, which is the same as weight multiplied by the height, which is equal to 500 multiplied by 5, which is equal to 2,500 joules. So he used 2,500 joules. It took him 5 seconds to do the job. So we can say that the power is the work or the energy divided by time, which is equal to 2,500 divided by 5. And this gives us 500 watts. So it's pretty straightforward. The answer is B. Now we have solved some problems about power. Stay tuned in the next videos. We will be revising the whole chapter just by solving as many problems as we can. See you then.